So what I'm going to cover next is a concept called maximum likelihood. Okay, so you're all probably familiar, or the way you normally look at statistics. You draw a distribution. Okay, you've got a mean and you've got a sigma, for example, a mean and a volatility for a normal distribution. So it's normal, and it's mu, and it's sigma. Okay, and what you're used to seeing is that you specify the mu and you specify the sigma in advance, and then you draw a distribution. Now, what if I gave you a series of returns? Okay, let's say 1,000 returns from the SPY, the S&P 500 index. If I gave you 1,000 returns and you did a histogram of those, okay, like we did in the lab, or some of you are going to do in the lab tomorrow, when you did the normality test and you saw that it wasn't normal, okay, but you end up with a sort of a histogram, okay, like this. You know, it gets smaller out in the. So a lot of the returns are around 0. Sorry, over there you probably can't see very well. Everybody more or less see that? So what we saw in the lab was that you ended up with some returns out here, okay, that were extreme returns, in particular on the left-hand side. Now, instead of starting with the mu and the sigma, okay, what if we try to get the mu and the sigma from these, okay? And that's what maximum likelihood does. Okay, so let's say we draw a distribution like this, and the distribution gives you a probability for every possible return here. You've got the return on the x-axis, and you've got probability on the y-axis. So let's say return 1 is here, okay, or 1. You've got a probability of or 1. Let's say return 2 is out here. There's a probability of or 2. Okay, and so on, up to or 1,000. Okay, dot dot dot. Probability of or 1,000. So the probability of seeing all of those is just the product of the probabilities. Okay, so that's a likelihood. That's the likelihood of seeing all of those returns. And when you calculate that probability, you use a distribution. If you change the distribution, the probability will change. Okay, and what you want is that the likelihood value, you want to pick the distribution that maximizes the likelihood value. Okay, so if you change the mu and the sigma on the normal distribution, it will change the probability of you seeing each of those returns. And a better one will give you a higher probability for each return. And then the likelihood of seeing that sequence of returns, or 1,000 returns, is higher. So if we did that, we would have selected the parameters, the mu and the sigma, by maximum likelihood. That's, you pick the parameters that make the likelihood of what you saw as high as possible. So you're putting all the weight in the data, you're letting the data pick the parameters. Okay? And that's what maximum likelihood is. So where are we going to see that? Well, when we do arch models and Garch models, how eViews fits those models, for example, is by maximum likelihood. So it's a more complicated likelihood function than this simple one, but it's still, the principle is the same. Okay. So there's nothing particularly fancy about maximum likelihood, and it may or may not necessarily give you the right answer. Okay. So this slide here, for example, let's say somebody arrives in New York, and all the taxi cabs in New York, they have registration numbers from 1 to n. Okay, so n is the total number of taxis. So let's say there's 30,000 taxis in New York, for example. N would be 30,000. Okay. So if you only saw one taxi, and the plate had a number 1,000, what would your guess of n be? Okay, by by maximum likelihood. That's, you know, this is an example to try and to bring that home. So in this case, we've got these probabilities of seeing each of one of these, and the probabilities are determined by the normal distribution. But if we've got 30,000 taxis in New York, the probability of seeing any one taxi, all other things being equal, is just 1 over 30,000. So the probability is given by 1 over n. It's a different distribution to the normal distribution, okay, that we're looking at. So the probability is 1 over n. Okay. So if you don't know what n is, in the same way that we pick mu and sigma, how would you pick n to maximize the likelihood of you seeing a particular taxi? How would you pick n? So if you see taxi number 1000, what value of n would you pick to make that as likely as possible, given the probability is 1 over n? So what's going to make the probability higher? If it's 1 over n, what's going to make it higher? A high value of n or a low value of n? A low value of n. What's the lowest value of n that you can pick? 1000, yeah, because we saw 1000. So the maximum likelihood value for n is 1000. So that's what your estimate would be. So if somebody said to you, I want you to use maximum likelihood to tell me how many taxis there are, you would just pick the one that you saw. Because it's the smallest one that makes the likelihood of you seeing that one as high as possible. Okay? So that's basically what maximum likelihood does. It picks parameters that make the data seem as likely as possible. And if you're using, for example, if you're using it to fit a normal distribution, it will pick the mu and the sigma that make the data as likely as possible. Also, if you're picking another distribution that might have a skewness input, so there might be 3 inputs, then it would select the 3 inputs that make it as likely as possible. Or you could have 4 inputs in a different distribution with skewness and kurtosis. And you can fit models using maximum likelihood as well. So basically, you're picking the parameters for those models that make the observations as likely as possible. Okay. So I asked this question last year, and people gave me some really random answers as to how to maximize the likelihood in this case. So. Okay. So the problem with using this type of a likelihood function, you can see these probabilities are normally quite small. Okay, so they're less than 1 anyway. And if you've got a lot of observations, when you multiply them out, you end up with a problem because you get very, very tiny numbers. They get smaller and smaller and smaller. You get really tiny numbers. So if you get the log of this, you probably know that the log of a times b is the same as log a plus log b. Okay? So that's why people use log likelihood. They get the log of each probability, and then they just sum them all. Okay? And that's just a better scale. Numerically, it's easier to deal with that. So whenever you look in eViews, you'll see a log likelihood reported rather than an absolute likelihood. Okay? Because every time you multiply a tiny number, you get something like 1e to the minus 15 or 1e to the minus 30, or you start running out. Numerically, you start running out of space to store them on. Okay. So it doesn't have this rapidly becoming small issue. So that's log likelihood and the principle of maximizing likelihood. So a related subject is information criteria. Okay, so these are used to select models. So in a similar way that you use the maximum likelihood to select models, people also use information criteria. All right. So you can see it's basically just the log likelihood function. Okay, it's related to the log likelihood function, and also it's related to the number of samples you have. So the bigger t is, the better. Okay, And also, it's related to the number of parameters you have. So the more parameters you have, the worse. Because, as I said before, there's more of a chance that you're data fitting when you include more parameters. So they're penalized in a lot of goodness of fit or information criteria. So in this case, T being big is good and K being big is bad. Okay? And I've already explained what the log likelihood function is. So really, you want this value to be as close to 0 as possible. Okay? Does anybody know why that is? So what if you had a probability of 1? You perfectly predicted every single return or whatever, and your likelihood was 1, the log of 1 is 0. Okay, so the log likelihood is 0 in that case. And as it gets smaller, it gets negative. Okay, so as you get less than 1, you start getting negative in the log space. So what you'll find is these values are minus something like minus 1400 or minus, and then you get another model and it's maybe minus 1300. And the minus 1300 is closer to 0, it's better. And you would pick that. Okay. So the two criteria are the Akaike information criteria and there's a Bayesian information criteria. And the difference between these two is that the second one penalizes the number of parameters more than the first one does. So it will pick a more parsimonious model. And I recommend that you use the second one. Okay, so you should penalize adding parameters. And you see the term parsimonious used. You should pick a parsimonious model, and it just means that the less variables you have in your model, for a given amount of explanatory power, the better. And if you start adding in variables, they better be strong, and otherwise you're overfitting. Okay? So people who actually trade their forecasts, or people who actually stand behind their models, as aside to people who just use them for research, they tend to penalize adding parameters because they've learned their lesson that basically you can get a very good fit historically, and then it doesn't work as well out of sample when you go to use it going forward, and it's because it's overfit, and it's a huge problem unless you've got a massive data set. Okay, so we're jumping around a little bit with these main concepts. So the next one, we're going to cover it again in another lecture, but it's stationarity. So people get confused about that as well. But the idea of stationarity is that a series doesn't go anywhere. Okay, so when you look at the residuals from a regression, if they're normally distributed, they're mean 0. Basically, over time, they're moving like this. They're around 0. Okay, they're not going anywhere. It's something that's non-stationary. It's sort of like wiggle around, but then it starts going somewhere. Okay, so it's moving away. So anything that has a trend, for example, is non-stationary. Okay? And that's the second one here. So let's say a stock price, S of t, it's the same as yesterday's price, plus an amount due to the time step, lambda t. So for example, that could be, it goes up 0.1% every week or something. Okay? So if you're looking at weekly data, the value this week is going to be the value last week plus 0.1% plus some kind of random term here. But the fact that there's a deterministic trend in there means it's going to go somewhere over time. It might move around a bit due to the random component, but over time it's going somewhere, and that means it's not stationary. Okay, the other one that's often used to describe stock prices, and this this started getting used back in the late 1800s. So there was a guy, Bachelier, who did his PhD thesis on describing stock prices, and he used geometric Brownian motion. And that's what GBM stands for there. It's a random walk. And in that case, the stock price today, it depends on the price yesterday. There's a little bit of a drift term there, and then there's a random term. Okay? And they're both scaled. The drift, you see the difference between these two is that this is mu times s. Okay, so let's say this mu is 1/10%. This is basically scaling by 1/10% times the stock price. So as the stock price gets bigger, this growth gets bigger as well. Okay? And the same with the variance. As the price gets bigger, the variance gets bigger. So that's a random walk, and it's sort of you get these kind of paths. That's what a random walk looks like. It's like geometric Brownian motion. If you've seen kind of where it comes from in Brownian motion originally, it's little pollen particles suspended in liquid, and they're bouncing around off each other randomly, moving in different directions. Okay, so those are two different types of non-stationary series. So before we would use these and do econometric analysis on them, normally you have to make the series stationary. Okay? So the way you would do that is to subtract the trend from this one. You could just subtract the trend, and then you'd have a stationary series. Or you could log difference this one. Okay? So the same way that you get the log difference to get returns, you go from price to returns, and this will be stationary once you got the log returns of this series. Okay, so these are examples of series that have a unit root. And what the unit root means is basically, if you look at this, S of t today is 1, it's a unit times S of t yesterday. Okay, and unit roots and unit root tests are checking for that. They're checking for a multiply by 1 value here. But we're going to go into that in more detail later. Okay, so this next section is on moving average processes. So we're going to cover two things. One is autoregression, which we cover in the labs, and with the residuals. And the other thing is the moving average. So we're going to look at the moving average first. And basically, an MA process is like this. So these U of t, or these errors, you can think of these as random shocks that happen. Okay, so you've got some kind of a model, like with the French model, we've got some kind of exposure to the market, to another factor, and then there's some kind of random shock that's just, it's not related to those factors, and it's normally distributed at mean 0. It's just random, so anything could happen. So, something completely unpredictable, like a terrorist attack or something, or it could have an effect on prices, and that's a random shock to something. Nobody predicted it, nobody knew. And what it's saying is that if there's a shock today, that it will affect not just today's price, but also tomorrow's price, maybe the next day's price. It's persistent, so the shocks themselves are persistent. So in terms of a regression, this is like having lagged residuals in your regression. And it's called a moving average process. And normally you have an NA bracket. So you've got like MAQ here, and the Q describes the number of lag terms. Okay, so if you've got 1 lag, it means yesterday's, 2 lags the day before, or the previous time period. So there's some statistical properties here of these models. Okay, I don't expect you to know these or to derive them, but you should know the effect that this would have if you didn't treat it. We didn't look at it. Okay, so the mean and the variance will change. Okay, and it also affects the autocorrelation of the series. So, for example, the stock price today isn't correlated with previous versions of itself. Okay, so I'm going to skip through this. I don't expect you to derive this. I put this in because it depends on some people like to understand things completely from scratch. And some people just want to be able to explain them. from a higher level. And on the course, this is a practical course. It's not, you don't have to theoretically derive these things. Okay, so just looking at this process, the original process, he's going to look at an MA2 process. Okay, so you've got two lagged residuals in there that are significant. And in this case, T1 is minus 0.5 and T2 is 0.25. So what these slides are showing is that this will lead to autocorrelation in the original variable. So x of t will suddenly become related to previous versions of itself. It will have autocorrelation. Okay? It will also affect the variance of x. So where sigma squared is the original variance, it's now being scaled, it's larger. Okay? So when you have these MA effects, you end up with a bigger variance than you originally had. Okay, so the expectation also changes. Okay? So looking at this ACF, what it means is basically how much is x of t correlated with the previous version of itself. So at a time step of 0, it's got a correlation of 1 to itself, because anything correlated is correlated to itself, with a score of 1. And then with a lag of 1, it's got a value of minus 0.4 something. Okay? And then with the second lag, it's got an autocorrelation of 0.2. And then after that, the autocorrelation disappears. So you can see the MA of 1 and MA of 2 has led to two significant autocorrelations in the original series. Okay. So when the variable is affected by shocks that are a day old or 2 days old, it will be autocorrelated with itself 1 day ago and 2 days ago. So autoregressive processes, these are very common in finance. So this is basically that the price or the return depends on a value plus it depends on the value yesterday or the value 2 days ago, and they're normally written as A or P. Okay, so if you were testing for autoregression, you would just test the dependent variable and lagged versions of the dependent variable, and you would check if this phi 1, phi 2, etc., whether or not they're significant. So you could possibly create a forecast for index returns based on yesterday's return and the day before's return. Okay, so here is the autocorrelation function and the partial autocorrelation function for an A or 1 model. Okay, so in this case, y of t is a half of its previous value plus a random term. And you can see that even though y of t, even though there's only one lag in this model, you get y of t correlated with older versions of itself, and it dies off gradually. Because if you look at it, you've got 0.5 times y of t minus 1, okay, but y of t minus 1 has got 0.5 times y of t minus 2 in it, and that goes on, that's a continuous series. So it decays off gradually like that. So even older versions or more lagged versions of the dependent variable become correlated with the current value. Okay? And if you corrected for it, it would remove all of that. Okay, so when we've got these A or MA effects, so remember autoregressive is where it depends on its own value previously, and the moving average is when shocks that happens historically, and remember the shocks are a part of the variable, not they're the residuals of a regression, for example. And and they also persist. Okay, but when you've got this information about a time series, you can start forecasting tomorrow's value. Based on the fact that some of the lags on today's value are going to determine tomorrow's value. So you can get some weak forecasting going, and even though it can be weak, it can often be better than using fundamental factors and macroeconomic information and things like that. So time series forecasting has become more and more popular. People have given up on using fundamentals because the fundamentals are normally priced in very quickly. Let's say there's an announcement, an FOMC announcement or something. That information gets priced in very quickly into the market. So it's very hard to act on it. Okay, so these things are useful for forecasting, but the number of lags is likely to be small because the markets are quite efficient. The other thing is the size of the importance, or the size of the coefficient on the lags might be small. So the lag might be significant, but the reason it's significant is that it's such a small effect that if you were to try to trade it, you wouldn't make enough money to cover your transaction costs. So people don't bother, they're not that interested, and it exists. So the markets are never fully efficient. They're only efficient to the extent that people are not motivated to go in and make them efficient. Okay, so that covered the AORMA models. We're going to cover those in the lab. It's part of your lab, and you're going to select an AORMA model using information criteria that we covered today as well. Does anybody have any questions on all of that? We covered a lot, we jumped around a lot, but hopefully I didn't go too quickly. Does anybody have any questions? We're going to cover all of this in the lab again anyway. And then we're going to get on to Garch models and Arch models, which are similar to ARMA models, but they're for the volatility rather than for the variable itself. So if you know what an ARMA model is, you can write out a Garch model very easily as well. Okay, so I'll leave it there, and I'll see some of you in the labs tomorrow. Yeah. I think we're next Wednesday. If anyone has any questions, come on.